All right, welcome to Unit 2, Exploring Two-Variable Data. In this video, we're going to focus on topic 2.6, Linear Regression Models. All right, so in this unit, or in this topic, we're going to use models to, model, right? That's what models are supposed to do. So far we've looked at scatter plots. We talked all about how to look at a scatter plot, how to read a scatter plot, how to discuss a scatter plot. We talked about correlation, which measures the strength of a linear relationship in a scatter plot. But now we want to say, hey, listen, I see a pattern here. Like, I see a relationship going on here. I see some type of connection between these variables. Can I model what I see and yet that model help me make predictions? I mean, in this scatter plot, I clearly see a positive, pretty strong linear relationship that shows as the temperature goes up, the sales of ice cream go up. But can I somehow model that? And I hope in everybody's mind right now, you're thinking about our old friend, maybe you learned this back in middle school, I don't know, a line of best fit. That's exactly what we want to do here, is we want to use a line of best fit. But a line of best fit is a very childish name for what we're going to do. We're going to call this a linear regression model. So what is a linear regression model? It's a simple linear regression model is an equation that uses an explanatory variable x to predict the response variable y. Now, unlike in algebra, a linear model can only take an x value and predict a y value. You cannot start with the y value and solve for an x value. So if we go back here, a linear regression model is literally a line, but we're not going to just call it a line of best fit anymore. We're going to call it a regression model. It is a linear regression model that can be used to take a temperature and predict the sales at that given temperature. All right, so here is what a linear regression model looks like. Yes, it is linear. It has a degree of 1. So the highest degree that you'll see on that x is 1. But we do write it in a little bit of a weird way, right? You guys are probably used to, back in algebra, writing y equals mx plus b. Well, we are not going to use that. Now, we're still going to use linear, right? The degree on that x is still a 1. So this is still a line, but we're going to write it a little bit differently. Rewrite it in the form of y hat equals a plus bx. So let's first talk about all the different items here. Now, first, x is the explanatory variable. In the picture that I've been showing you in the scatter plot we looked at, that would be temperature. Now, y hat, it's important, and that hat on there is actually really important. It is to understand that this is just a prediction. This is not an actual value. This is just a prediction. Remember, that's all what we're doing here. We're modeling data. We're not telling you exactly what is going to happen. We're just modeling what we think may happen based on a trend that we're seeing. So it's important that that hat is on the y to represent the fact that it is predicted. Now, those are the two variables, right? Every linear regression model in this world is going to have an x and a y hat. I promise you. Every linear regression model will have an explanatory variable and a predicted response variable from the linear regression model. But the other variables end up being actual numbers, right? In a specific problem, these will be numbers. And that is A, the y-intercept, which I know is a little bit confusing because if you remember, we used to call B the y-intercept, but that was back in algebra. We're in statistics class, right? So A is the y-intercept, and we actually write it first. And then B is the slope. So A is the y-intercept that we write first, and then B is the slope that is being multiplied by x. So the actual variables of the problem are the x and the y hat, and then A and B are actually in a real problem become numbers. That way we could then plug in an x and get a predicted y. All right, so this is what you guys have called the line of best fit before, but again, we're using a little bit more of a mature statistical name, and that's called a linear regression model. So the points in the scatter plot are the actual values from the actual individuals that are measured, and the line is simply a model that can be used to make predictions about y with a given x. All right, so how do I know a linear model is appropriate? This is super important. Like if we go back to the scatter plot for 1 second right here, how do I know that making a line is the appropriate thing to do? Well, this is where we get correlation, right? We think correlation coefficient close to 1 or -1 does not simply mean that a linear model is appropriate. Sometimes curves can hide in data, and even slightly curved data could still give a strong correlation. But remember, correlation is only used for linear data. So to know that a linear model is appropriate for your scatter plot, first and foremost, your scatter plot should look like it's at least somewhat linear. We will explore this idea even more in the next topic. But go back to this scatter plot right here. How do I know putting a line through my data is the appropriate model? Because it looks linear, right? I don't see a giant curve. If I saw a scatter plot and that scatter plot had a giant curve in it, I don't think it would be intelligent to try to put a line through data that is curved. That would be a stupid idea. So, oftentimes we want to say, hey, is it intelligent? Is it smart? Is it appropriate to use a line for this data? Well, the first thing I hope you mention is yes, because it looks straight. It looks like a line. If your data doesn't look like a line, don't use a linear model, okay? A lot of times kids want to jump to correlation. They want to say, yeah, the correlation is strong. It's 0.9. Let's go ahead and make a line. Well, like I mentioned, just because your correlation is close to 1 or -1 does not mean that a line is appropriate, because sometimes there could be a curve, and a curve can still give you a good correlation. But remember, we stressed in the last topic that correlation is only used. I don't care if you find correlation for curved data. You wouldn't use it if the data is curved. Correlation is only used if your data is linear. All right, so let's look at like a solid example here, right? All right, so in this example, what we looked at are 16 Ford F-150 4x4 Super Crude trucks that are for sale. And for every truck, we looked at how many miles were on that truck, how many miles has that truck driven, and then we looked at the price that that truck was selling for. So we have 16 values here, and I already went ahead and made a scatter plot for you. So, is a linear model appropriate? Well, I don't see a giant curve. Do I see a perfectly straight line? No. The correlation is probably going to be negative. Well, I hope the correlation's negative. It's definitely going down, right? Is it going to be -1? No, I don't see a perfect straight line. But it looks pretty linear, right? Like I definitely see a negative trend. I definitely see a line. I don't know, maybe -0.7 would be a good correlation here. That's not weak by any means. Is it super strong? No, but it's good, right? I definitely see something linear going on here. I definitely see a linear pattern. All right, so this is a scatter plot, right? Every dot represents an actual truck. It represents the miles on that actual truck and the price of that actual truck. Well, what if we want to create a model that we could use to help maybe make some predictions, right? Like I give you the miles on a truck and you could use the model to predict the price. Well, boom, here it is. Here is our first example of an actual linear regression model. So graphically, you could see the line. It's in red, pretty obvious. And then up here, I actually have what the model is. So y hat equals 38257 minus 0.1629x. So let's identify the variables. The variable are x and y hat. X is the miles, and y hat is the predicted. It's so important that you put that hat on there and say predicted price, because no one is saying that anything is going to be guaranteed. The only things that are guaranteed are those blue dots. The line, the entire line is nothing but predictions. No one knows for sure if those predictions will come true. Now, those are the variables, right? The A, now that's an actual number now. That is 38257. That's the y-intercept. Remember, a y-intercept is what happens when x is 0. So if a car has 0 miles, it is predicted that it's going to cost $38,257. The slope is b, and the slope is negative 0.1629. Now, what the slope tells me is that for every 1 mile that a car or a truck gets added onto it, it is predicted that the price is going to drop about 16 cents. So remember, slope is something that continues on. It's for every one, this, right? So as we move left to right, as we add a mile onto a truck, its price will decrease, predicted, not actual, this is just predicted, by about 16 cents. The negative is what tells me it's going down. Now, so it's really important that you understand all of the numbers and letters in this equation. X and Y are the letters, those are the variables, and then the actual numbers are the slope and the y-intercept. The other thing you could do is you could personalize it. So instead of saying y hat, you could say price hat. So that's the predicted price. And then instead of saying times X, we could say times miles driven. That makes it super clear what X is and what y hat is. Now, a little question I put down here in the bottom is most kids, I hope, if you're really paying attention and really thinking, you're wondering, where did this equation come from? Like, all right, great, Mr. Prenjak, you're showing us this, you're telling it, but where'd it come from? Well, that's a really good question. I'm going to save that for a couple topics from now. So we will eventually cover where this equation comes from, and we are going to learn how to find the slope and y-intercept on our own. But for right now, I just want you to understand in this video what a linear regression model is. And for right now, I will give it to you. I just want you to know what it is, what it represents, and what we could do with it. So what are some things that we could do now that we have our linear regression model? Keep in mind that this is a model that is used to predict the price of a Ford F-150 truck based on the miles driven. Well, we can actually use it, right? Like, let's use it to make a prediction. So let's predict the price of a truck with 100,000 miles on it. All right, so the Y hat is going to be 38,257 minus 0.1629 times, I'm going to now plug in the miles driven, 100,000 miles. All right, now I'm just going to go to my calculator, and I can type this in all at once, right? It's not very complicated. 38527 minus 0.1629 times 100,000. And I get $22,237 as the predicted price. Don't say anything that would allude to you believing that this is the actual price of a truck with 100,000 miles. This is nothing more than a prediction based on a model that was founded from my data. So if you are, going to buy a new truck and has 100,000 miles on it, I am simply predicting that it will cost $22,237. I'm not saying that it will cost that. Now, I said this earlier, and I want to actually emphasize it now, again, that you might have a better understanding, is that these equations cannot go backwards. Don't be fooled, because I will try to fool you. Don't get fooled. If I said something like, hey, there's a car that's for sale for $25,000, can you take the price of $25,000 and predict the mileage? The answer is no, I cannot do it. This equation is literally built, and we're going to learn how to build it later, but it is built to do one thing and one thing only. You plug in the miles on a used truck, and it tell you the predicted price. It cannot work backwards. Basically, it comes down to the idea that $25,000 was an actual price. If you found that labeled on a truck, that's an actual price. You cannot plug an actual price in for a spot that is reserved for a predicted price. And that is why the hat on that Y is so important to understand that that is a predicted Y value. All right, so these equations cannot work backwards. All right, one more really important thing is extrapolation. Be careful here. So extrapolation, maybe you've heard that term before, but extrapolation is predicting a response variable using a value for the explanatory variable that is beyond the interval of x's used to determine the regression line. You might be like, what? Okay, let me go back and explain. All right, if we go back to our equation, this equation that I still have yet to tell you where it came from, I'm just kind of giving it to you right now, free of charge. But this equation is actually from using these blue dots, right? So these blue dots together are able to create this equation. And the issue is this. These blue dots came from looking at cars as low as maybe 8,000 miles to as high as somewhere around 130,000 miles, 140,000. You can actually go back to the data if you want. You could look at our lowest mileage was around 8,000 miles, and our highest mileage was around 144,000 miles. The point is that the data, the line, the regression model was created based on this data. So extrapolation is trying to make a prediction with an explanatory variable that is outside of our data range. So if I said to you, hey, what's the predicted price for a brand new truck with 0 miles on it? Well, our data didn't come from trucks with 0 miles on it. So I would not rely on using my equation to predict the price for a truck with 0 miles on it. None of our trucks had anywhere near 0 miles on it. Or I could go the other way. I could say, hey, what's the price of that truck with 300,000 miles on it? Well, our data didn't come from trucks with 300,000 miles on it, so I don't think making a prediction about that would be very reliable. Now, nothing is handcuffing me from using this equation and plugging in 0 miles or plugging in 300,000 miles. I could do it, but it just wouldn't be a very reliable result. So again, look at your data. Here's the original data. And this equation that I came up with, the linear regression model, is really only best used for X values that are near my data, if that makes sense. So extrapolation is reaching outside of your data. Trying to make a prediction outside of your data is not recommended. You might get a value that is not reliable, and the further you try to reach outside of your data, the more unreliable that your answer is going to be. So keep in mind that when this linear regression model is created, it's created from your data. So use it for data that's like your data. So 100,000 miles, that was good, right? 100,000 miles is in the middle of my data. Yeah, I didn't have any data necessarily at 100,000 miles, but I had some data above and I had some data below. So using my model to predict 100,000 miles, that's a pretty good idea. Even 50,000, 75,000, any value in our data is smart to use our model for. It becomes unsmart when we try to make a prediction outside of the scope of our data. And that would be numbers too low or numbers too high. So don't do that. Watch out for that. And it's not a trick. Like, I'm not going to try to trick you by saying, hey, use this equation to predict the price of a truck with 300,000 miles on it. I might ask you that, but it's not a trick. I want you to recognize, hey, none of my data was near 300,000 miles, so I should be very skeptical of using my model to make that prediction. All right, so hopefully you understand how easy a linear regression model is. It's simply the equation of a line, which you guys have been working with all the way back since your algebra days. Now we just got to make sure that we understand that this is a very specific line that is used to model data that we created from our sample, okay? So hopefully that was pretty painless. I mean, this actually is a very easy topic. There's really not a whole lot we could do other than use the equation. Just be careful that you use it appropriately. You don't use it backwards and you don't extrapolate. All right, guys, see you in the next video.